Okay, so now that we have defined the game, let's move on to strategies and Nash equilibrium. So, in this game, a strategy, in a pure strategy, is going to be a function that assigns to each information set for player I, each II, an action in a II. So for player 1, the only II is the null set, and so the strategies will just be either C, D, or E. Right? Just playing C is a strategy for player I, for player 1. For player 2, the strategy has to specify what player 2 does in this information set, which contains C and D, and what player 2 does in this information set, which only contains E. And so for player 2, the strategies will be either FH, that's a valid strategy, playing F here and H here, GH, FI, or GI. A mixed strategy is just a probability distribution over pure strategies. So a mixed strategy, for instance, here could be playing a mix between FH and GH, or playing a mix between all four of them. A Nash equilibrium. So a mixed strategy Nash equilibrium here. For that, just look at the definition on page 318. Let's see if you can see this. This is definition 318.4. Basically, what it says is that alpha star, a mixed strategy, is a Nash equilibrium if and only if the utility that player I gets from playing alpha I star, so its role in that strategy profile, where the other players follow their own strategy profiles in alpha star, is at least as much as player I would get from playing any other strategy, given that the other players still play alpha minus I star. And this, if it holds true for all alpha I available to player I, and for all player I's, then alpha star is a mixed strategy Nash equilibrium. Remember, a pure strategy Nash equilibrium is just a special case of a mixed strategy Nash equilibrium in which each strategy is played with 100% probability. Right, so this definition works perfectly well for pure strategy Nash equilibrium. If you want a separate definition, then all you really have to do is get rid of this, right? Pure here. Instead of alpha, we've been using A for pure strategies. This becomes A I star. This becomes A minus I star. This becomes A I star and A minus I star. And that has to hold for all AI and for all I. That's pretty much it. That's the only difference. Let's go further. Let's see how to calculate the Nash equilibrium for that game. Okay, we already know what the strategies are, so all we need right now is the payoff matrix. Let's see. So for player 1, we've got C, D, or E, and for player 2, we've got F, H, F, I, G, H, G, I. Okay, player 1 plays C, player 2 plays F, we get 3 and 3, 3 and 3. Player 1 plays C, player 2 plays G, we get 1 and 1, 1 and 1. Player 1 plays D, player 2 plays F, we get 4, 3, 4, 3. This becomes 0, 2, 0, 2. Player 1 plays E, this H is relevant, so then that comes to 4. EI is 3, 3, 2, 4, 3, 3. And our way of denoting best responses is exactly the same as what we did earlier. If player 2 plays FH, then player 1's best response is 4, is playing D. GH best response is E. GI best response is E. If player 1 plays C, then player 2's best response is either FH or FI. Player 1 plays D, player 2's best response is either FH or FI. Player 1 plays E, player 2's best response is either FH or GH. And so we have 3 Nash equilibria, which are D, FH, D, Fi, and E, GH. And those are the Nash equilibria of this game. However, like before when we had extensive form games, some Nash equilibria made sense, while others didn't. And the way we refined Nash equilibria away then was by invoking subgame perfect Nash equilibria, subgame perfection. Here, there isn't a proper subgame of this game. This alone, let me just draw that circle. This is not a subgame. Anytime you intersect an information set, that's not a subgame. Right? But we do run into a problem in this game. The problem is equilibria like EGH make no sense. If player 1 chooses either C or D, irrespective, player 2 is better off playing F, right? Because 3 is greater than 1 and 3 is greater than 2. If player 2 is always going to play F, if player 1 plays either C or D, right, then by playing either one of them, player 2 can earn either 3 or 4. In this equilibrium, EGH, player 1 is choosing E, knowing that player 2 would choose H, right, because 4 is a greater number than 3, and thereby earning 2. Why would player 1 ever do that? Choosing C or D is better. However, EGH is still an equilibrium because if player 1 is playing E, player 2 can do no better by deviating away from GH. And if player 2 is playing GH, player 1 can do nothing better than playing E. What we want is some sort of requirement that players play optimally after every information set. Here we can impose that because we have a clear optimal, but we won't always be able to enforce it so clearly, and so we will also need a notion of beliefs. That notion will come in, it'll become really important in games like this. Let's say this is 0-3 and this is 4-2. Right? Then F is optimal if player 1 plays C, but G is optimal if player 1 plays D. And what's optimal for player 2 to do will depend upon what player 1 believes player 1 has done. What player 2 believes player 1 has done, right? Whether player 2 believes that player 1 has played C or D. And so we would need a belief system which tells player 2, which gives player 2 a probability distribution of the histories that are contained within this information set. Let's do another quick example. So for this game, we found these Nash equilibria. I hope everybody's on board with that. If not, talk to me during the Zoom meetings. Remember this game? This is the Bach or Stravinsky game, where you had a 2-1-0-0-1-2-0-0 Bach Stravinsky. We can also write this out equivalently as this game, where player 1 first chooses either Bach or Stravinsky. Player 2 doesn't know whether player 1 has chosen Bach or Stravinsky, but player 2 has to again make that choice between Bach and Stravinsky. And the pairs to BB, it is 2, 1, BS is 0, 0, SB is 0, 0, and this is 1, 2, SS. And these two games are actually equivalent, right? Even though here we have simultaneous moves, here these moves are played as if they're being played simultaneously. Player 1, when choosing between B and S, doesn't know what player 2 has chosen, and player 2, while choosing between B and S, doesn't know what player 1 has chosen. And so, actually, we end up with the same Nash equilibria. The pure strategy Nash equilibria are BB and SS. And the mixed strategy Nash equilibria will be ones where player 1 plays B with a probability 1/3, S with a probability 2/3, player 2 plays B with a probability 2/3, and S with a probability 1/3. Or something like this. You've done this before, so you can go over your notes, but I think if player 2 is playing this 2/3 of the time, oh no, this will be 1/3. And if player 1 is playing this 1/3, yep, 2/3. So this is the probability distribution that player 1 would put between B and S, between playing these two. And this is the probability distribution that player 2 would do between B and S. And that would be a Nash equilibrium. Yeah, so those would be the Nash equilibria of this game. See you in the next video.